So, good afternoon. Today is the week 11 of the live interactive session for the NPTEL course Introduction to Atmospheric and Space Sciences. So, last class we were mostly discussing about the ionosphere, which is one of the topmost layers in the atmosphere. And we also discussed what are the different types of layers in the ionosphere, how the layer characteristics are changing when during daytime, nighttime, and how it is changing during different based on the solar cycle, etc. So today we will be continuing the discussion about the ionosphere. So as we discussed, ionosphere, it is a region in the Earth's atmosphere where electrons and ions are present in large numbers to be able to influence radio wave propagation. So basically it is a layer in the atmosphere where large number of electrons and ions are present, and this layer plays a major role in the radio wave propagation and communication. So it basically extends from 60 kilometer to 1000 kilometer. That is topmost part of the mesosphere and the thermosphere, and it acts as a reflecting mirror layer. It acts as a reflecting mirror because the emitted radio waves are basically being reflected back to the surface itself by uh, this layer. It helps in reflecting signals, the wave signals, which is used for in communication. The reflection of these radio waves is determined by the refractive index of the medium, and in the ionosphere the charge density, which is basically depending upon the charge density. In case of the ionosphere, the refractive index is basically determined by the charge density in each layer, and the charge density is not the refractive index determines the reflectivity of the radiation, and the charge density determines the refractive index of that particular layer. the charge density is not constant in the ionosphere. It varies from one layer to the other. So basically the different layers in the ionosphere is determined by their electron density, or characterized by their electron density. One layer to the other. And based on this charge density and altitude in the ionosphere has been divided into different layers. So basically, ionosphere is a region in the atmosphere where a large number of electrons and ions are present, and these layers are basically capable of influencing the radio wave propagation. It basically extends from 60 km from the surface to 1000 km, which is basically the topmost part of the mesosphere and the thermosphere above it, and it acts as a reflecting mirror layer. Basically, it helps in reflecting radio wave signals, which is used for communication. And the reflection is basically determined by the refractive index of the medium. So, in the ionosphere, since different layers have different charge density, the refractive index is basically determined the charge density of that particular layer. And in the ionosphere, the charge density is not constant; it changes from one layer to the other. And the different layers in the ionosphere are basically characterized by different electron densities. Based on altitude and the respective electron density in each layer, it has been divided into different sublayers. The ionosphere has been divided into different sublayers. Now, how this radio wave propagation is occurring in the ionosphere? So, we can see radio towers in the surface, which are located on the Earth's surface. We can see the radio towers which are located in the Earth's surface, like this one and this one. These radios are basically sending signals to each other. Suppose these two these towers are close to each other. Suppose these two towers are close to each other. If it is close, then it allows for the transfer of it allows for the wave propagation between them through line of sight propagation. Straight. If it is not that far away from each other, it will not be affected by the curvature of the Earth. So if it is one tower is here and one tower is here, it can directly send it like this. The issue comes when the towers are situated very far apart from each other. Suppose one tower is here and there is another tower here. So if you send a signal directly from this tower to this tower, it won't reach because of the curvature of the Earth. Because of the geometry of the Earth, you're not able to have inline or line of sight propagation between towers which are far apart from each other. So in that case, the waves from the tower is basically sent up to the atmosphere. The ionospheric layer, which is present in the topmost part of the atmosphere, reflect the layer back, and finally it reaches the tower. It basically reaches the receiving tower. So we have to optimize the wavelength and frequency of the radio wave that we are sending to the atmosphere based on the distance between the two towers, so that it will reach the receiving tower. It will basically reach where we want the radio wave to be sent. So basically the frequency and wavelength of the radio wave that are being sent by the tower yeah. So the frequency and wavelength of the radio wave that is being sent from the tower uh, should be optimized based on the distance between the sending and the receiving tower. So the radio waves are of very high energy. It may escape from the atmosphere, that it will go outside, it will penetrate the atmosphere and then go. If the wave that is being sent is of very high energy, and suppose if the wave that being sent is of very low energy, then it may reflect from the, if we send it, it may reflect from the lower layers itself, and it won't be reaching here. So based on, so we have to, if we basically want to send a signal from here to here, then it should not penetrate through the atmosphere, and also it should not get reflected from the lower layers of the atmosphere. So based on the distance between the two towers, we have to optimize the wavelength of the radio waves, the energy of the radio wave that is being sent. So now, how the density of the electrons in the ionosphere vary with respect to height. So that's how ionosphere helps in radio wave propagation. Now let's see how the density of electrons vary with respect to height in the ionosphere. So this is how the density of the electrons is denoted. This basically indicates the number of electrons per unit volume. This is how it is denoted. Now suppose this x-axis shows the electron density and the y-axis shows the altitude. This is how the electron density varies with respect to height in the atmosphere. So it keeps on increasing with respect to height and then reaches a maximum and then starts decreasing. The density of electrons, so this shows the density of electrons with respect to height in the ionosphere. So basically the density of electrons increases with height and reaches a maximum that maximum value of electron density is around 10 raised to 12 meter per meter cube, and the height at which this peak density is occurring is basically 250 kilometers from the surface. So this is how the electron density changes with respect to height in the ionosphere. The electron density increases with respect to height, reaches a maximum value of 10 raised to 12 number of electrons per meter cube at a height of around 250 kilometers and then starts decreasing. So why such a profile is seen for the electron density? So if we compare basically for the production of electrons or the electron density basically depends on two things. One is the neutral atoms, which is basically required to produce these electrons, and another one is the intensity of incoming solar radiation. Intensity of incoming solar radiation. So first let's see how the concentration of neutral atoms is changing in the atmosphere. We compare the vertical profiles of both the electron density and the neutral atoms. It will come like this. So this is electrons, this is altitude, this is how it has changed. This is a vertical profile in case of number of electrons in the atmosphere. Now if we look at the neutral atoms present in the atmosphere, how it is changing with respect to height. It is basically exponentially decaying with respect to height. So if you remember, we have learned how the pressure is decaying with respect to height in the atmosphere. T is equal to T0 e raised to minus z by h. And we have also learned that this is basically similar to the density, the change in the density of the atmosphere. How the number of molecules present in the atmosphere is changing with respect to height. It also follows the same equation, and the number density also follows the same equation. N is equal to N0 z by h. N0, N is the highest near to the surface. Whereas in case of, so as we go up in the atmosphere, the number of neutral atoms keeps on decreasing. The neutral atom decreases with respect to height. And we know the intensity of incoming solar radiation will decrease with respect to, will decrease as the distance from the sun is increasing. So basically the intensity will be highest at the top of the atmosphere. So this if we consider the height from the Earth's surface, basically the intensity of incoming solar radiation increase. Intensity of incoming solar radiation increases with respect to height from the Earth's surface. So since both are having opposing profiles, opposing vertical profiles in the atmosphere, both of them are maximum or enough incoming intensity of incoming solar radiation and enough number of neutral atoms are present at approximate height of 250 kilometers. That's where we are getting maximum electron density at that particular height. Now let's see how the ions are basically produced in the ionosphere. How do we get these the electron density? So I told you that the electron density is basically dependent upon two things. One is the concentration of neutral atoms in the atmosphere, and another one is the intensity of incoming solar radiation. So how the ions are produced in the ionosphere? So basically the ions are produced through a process called photoionization. By the incoming solar radiation. The ions are produced by a process called photoionization by the incoming solar radiation like extreme UV rays, extreme UV and X-rays. So if you write, we can write H nu, which is basically the photons of the incoming solar radiation, interacts with neutral atoms present in the atmosphere to produce ions plus electrons plus some amount of energy. So this equation basically represents the photoionization that is taking place in the ionosphere to produce ions. So So basically the photons in the incoming solar radiation interacts with the neutral atom, knocks off the electrons from it and produces an ion, an electron with some amount of energy. Yeah, so since the incoming solar radiation has maximum amount of energy, so this is how ions are produced in the ionosphere. And since the incoming solar radiation has maximum amount of energy at the top of the atmosphere, maximum amount of ions are located in the topmost part of the atmosphere. And as we go towards the lower altitude, the photons get absorbed or have been already used up for ionization in the upper layer, and hence the electron density decreases. That is the reason for the obtained flow. So since the incoming solar radiation has maximum amount of energy at the top of the atmosphere, H nu will be maximum number of photons will be maximum. Photons will be maximum at the top layers of the atmosphere. That's why maximum amount of ions or the ionosphere is basically present in the top at the top of the atmosphere. As we come down, as we come to lower altitude, what happens is that the number of photons either get absorbed by the atmosphere or it would have been already used up for ionization in the above layer. So enough amount of photons doesn't reach the lower layers of the atmosphere so as to cause ionization of the lower layers. So that's what photoionization, and that's how the ions are produced in the ionosphere. Now this thing we have, if you look at the profile that the profile for the vertical profile of electron density for the ionosphere, we can see that there are these inflection points where the slope of the there are certain inflection points in the vertical profile where the slope of the electron density curve is changing. So based on these inflection points, the ionosphere has been divided into different layers. The lower layer is known as the D layer, which is present, which is having an electron density of approximately 10 raised to 8 to 10 raised to 10 per meter cube. And the second layer is the E layer, which is having an electron density of approximately 10 raised to 11 per meter cube. And then we have the F1 layer, where the electron density is around 10 raised to 11 to 10 raised to 12. And then we have the F2 layer, where the electron density is maximum, around several 10 raised to 12 per meter cube. That is the F2 layer. So we have four different layers in the ionosphere. The lowermost layer is the D layer, then we have the E layer, then there is F1, and on the topmost layer is the F2 layer. You can see it from here also. So the D region basically extends from 60 to 90 km in altitude, and the peak production occurs around 90 km. Then we have the E layer, which basically extends from 90 to 140 km, where the peak production occurs at a height of 110 km. And the number density of electrons in the D layer is between 10 raised to 8 to 10 raised to 10 per meter cube, and in the E layer it is 10 raised to 11 meter cube, and in the F1 layer, which extends from 140 to 200 km in altitude, the peak production happens at a height of 200 km, and the electron density is between 10 raised to 11 to 10 raised to 12 per meter. And then we have the F2 layer, which is basically at a height above the which is basically the topmost layer, which is at a height of greater than 200 km. The peak production occurs at a height of 250 km, and the density is approximately 10 raised to 12 per meter. So they act as the different layers in the atmosphere. Now let's see how the reflection of radio waves happen in the atmosphere. Reflection of radio waves in the atmosphere. Why do we use radio waves for communication? Why radio waves are used for communication? Why can't we use any other waves in the electromagnetic spectrum? So higher the frequency of the wave that we are using, higher the frequency of the wave that we are using, higher the chance it will penetrate deeper into atmosphere. Higher the frequency of the wave that we are using, higher the chance it will penetrate deeper into the atmosphere. And if the frequency is so it should be an optimum frequency so that it won't penetrate, but it will reflect back into the surface. So if we look at the electromagnetic spectrum, we have gamma rays, X-rays, UV rays, infrared, microwave, and then we have radio waves. This is based on wavelength. Frequency, it will be the other way around. So radio waves have the lowest frequency and the highest wavelength. So E, the energy associated with the waves is basically given by E is equal to h nu or E is equal to hc by lambda. So lower the wavelength, or higher the wavelength, lower the energy. Higher the wavelength, lower the energy. So the waves won't penetrate through the atmosphere. Instead, it will reflect back. So radio waves, in case of radio waves, as we can see, lambda is very high, wavelength is high. So E, energy associated with it is very comparatively low. So it does not penetrate through the ionosphere, instead it gets reflected back. And also it also has a very large spectrum of wavelengths. So we have enough number of wavelengths to which falls within the radio waves, from which we can choose the optimized wavelength which can be used for propagation. So suppose this is the Earth, we have a point A over here and we have another point B over here. Okay. So consider this as the D region in the ionosphere. We already discussed like there are different regions in the ionosphere, which is basically determined by the charge density, characterized by different electron density in the layers. So suppose this is the lowermost D region, and then we have the topmost F region. Suppose this is the F region. So from A to B, if we want to send a signal, the wavelength should be, it can be reflected back from the D region itself. If it is reflected back from the D region, it will reach B. Suppose if we want to send a signal to another point, which is C. So in this case, the reflection from the D region will not cover this distance between A and C. So in that case, the reflection should be from the higher levels in the atmosphere, which is basically F region, E and F regions in the atmosphere. So in this case, the reflection should be from higher levels. So based on the distance between the towers, we need to determine the energy of the radio waves that are being sent. So from A to B, distance is less. So energy would be less. Reflection from lower layers. Now if we are sending from A to C, distance is higher. Higher frequency or higher energy. Reflection from higher layers. Now what is the reflection criteria? How can we determine the frequency at which the radio waves has to be sent so that it will be reflected from the particular region that we want? So what is sorry. So what is the reflection criteria? So the reflection starts at the critical frequency. Reflection happens at the critical frequency. The frequency at which the reflection happens is known as the critical frequency f0, which is when the radio wave frequency is equal to the plasma frequency. Plasma is the matter which consists of both charged particles of ions and electrons. So the ionosphere is basically plasma. So when the frequency of the radio waves is equal to the plasma frequency, at that time the reflection happens. So ionosphere is basically plasma. The ionosphere consists of plasma, which is basically which has both ions and electrons. So how to find the critical frequency? Critical frequency is given by f0 is equal to 9 under root of 10 raised to minus 6 into n. Ne is the number of electrons present in that particular layer or in the atmosphere. This basically gives you the answer in terms of megahertz, and the value of Ne should be given in centimeter raised to minus. So when the frequency of the radio waves becomes equal to the plasma frequency, at that time the reflection occurs. So the plasma frequency or the critical frequency f0 is basically given by 9. Plasma frequency is basically given by 9 into root of 10 raised to minus 6 into Ne, where Ne is the number of electrons present in that particular layer. So the result of this equation will provide you the frequency in terms of megahertz, and you have to give the number of electrons and centimeter raised to minus 3. So when f is equal to f0, f is the frequency of the radio wave, f is equal to f0, the radio wave reflects back. What happens if f is greater than f0? If the frequency of the radio wave is greater than the plasma frequency, then wave will penetrate. Instead of reflecting, it will penetrate into the atmosphere. And if f is less than f0, doesn't have enough energy, then what will happen? Wave will be reflected back by the lower layers. Like it won't reach that particular layer where we want it to be. It may get reflected back from lower layers. So f should be equal to f0. The frequency of radio wave should be equal to the plasma frequency for the reflection to occur. Let's solve one question regarding the critical frequency. The question is, calculate the critical frequency f0 if the number of electrons in a layer is 3 into 10 raised to 13 per meter cube. So we want to calculate the critical frequency and the number of electrons in the layer is given. So f0 is given by 9 into root of 10 raised to minus 6 into Ne. N is the number of electrons in that layer. Ne is given in the question as 3 into 10 raised to 13 meter raised to minus 3. As I said earlier, we have to give Ne in centimeter raised to minus 3. So if we convert this, so 1 meter is basically 10 raised to 2 centimeter. So 1 meter cube will be 10 raised to 6 centimeter cube. So 3 into 10 raised to 13 meter raised to minus 2 is 3 into 10 raised to 13 into 10 raised to 6 centimeter raised to minus 3. It will be 3 into 10 raised to 7. 10 raised to minus 6. It is minus 3 centimeter raised to minus 3. It will be 10 raised to minus 6. So it will be 3 into 10 raised to 7 centimeter raised to minus 3. Now f0 will be given as 9 into root of 10 raised to minus 6 into 3 into 10 raised to 7 centimeter raised to minus 3, or it will give you 9 into root of 30, which will be 40 root of 40 square root of 30 will be around 5.47 or something. So it will be 9 into 5.47, which will be around 9 into 5.47, be around 49.2. 0.23 megahertz. So this is the critical frequency for a layer, which is basically having a number density of 3 into 10 raised to 13 meter raised to minus 3. So approximately 50 megahertz. The radio wave frequency should be approximately 50 megahertz to be for it to get reflected by this particular layer. So now so we know that during daytime, so as we have already discussed, so we are familiar with the idea that during daytime, solar radiation is interacting with the neutral atoms and producing ions and electrons in the atmosphere and the ionosphere. So basically H nu plus a neutral atom gives an ion plus electron plus the energy, right? So this is constantly happening in the ionosphere. Along with this, constant recombination, along with this photoionization, constant recombination of ions and electrons back into neutral atoms or molecules. Constant recombination is also taking place along with this photoionization. So the ions and electrons are combining and forming neutral atoms in the ionosphere. So some of the reactions, we'll just look into some of the recombination reactions that takes place in the ionosphere. So we know basically the incoming solar radiation interacts with the neutral atoms or molecules, then knock off electron from it, and then produces an ion, electron, and some energy. This is constantly happening in the ionosphere, and along with this recombination of these created ions and electrons, they are combining back and creating neutral atoms or ions again in the ionosphere. So some of the recombination reactions that is happening in the ionosphere are some of the reactions. First one is a radiative recombination. Which means the ion which is formed by the photoionization combines with the electrons to form neutral atom plus a photon. So this is in the radiative recombination. The ions and electrons combine. Simply they combine with each other and produce a neutral effect and energy. So this is basically a very slow process. This reaction is very slow. Takes place in hours. So take hours for this reaction to occur. So that is radiative recombination. Now we have dissociative recombination. Dissociative recombination. In this case, what happens is that suppose a molecular ion combines with electron to give. So instead of an ion, atomic ion, a molecular ion interacts with an electron and produces two atoms separately. The molecular bond will be broken and it will dissociate into. So here the recombination of the molecular ion and electron is happening, which basically results in the dissociation of the molecule into two neutral atoms. So this is basically a fast process. This is comparatively fast, takes place in seconds. This takes place in seconds. So dissociative recombination is faster compared to radiative recombination. So in this case, molecular ion combines with an electron to produce individual neutral atoms. Molecular bond is broken and it produces individual neutral atoms. Now the third one is a charge exchange process. Charge exchange process. In this case, the molecular ion interacts with an electron. So charge exchange process. In this case, an ionized molecule interacts with a neutral molecule and will give you a neutral molecule and a charged. So in this case, the charge of this particular molecule is being transferred to another molecule. So the charge is being exchanged. So this is a charge exchange process. And the fourth one is the atom ion exchange. Fourth one is the atom ion exchange. In this case, what happens is that the ion combines with the molecule to give you XY plus Z. So one atomic ion or ionized atom combines with a neutral molecule and the molecular bond between those two atoms will be broken and the ion combines with one particular atom in the molecule and then the other atom becomes the atom. So the exchange is taking place and also the molecular bond between the molecule YZ molecule is broken and a new molecule is getting formed. So this is atom ion exchange. So these are the four different recombination reactions that is happening in the ionosphere along with photoionization. So radiative recombination, dissociative recombination, charge exchange process and atom ion exchange. So the top two is the important one, that the radiative recombination and dissociative recombination are the important. So now let us look at what is the time scale time scale associated with the recombination process. Each recombination process will have a time scale associated with this. So what is the time scale associated with the recombination process? Time scale associated with the recombination process in the mRNA. So the recombination time scale tau is given as tau is equal to alpha, which is basically the recombination rate, in the total number of electrons, the whole raised to minus 1, which is given in seconds. So alpha is the recombination rate, which is having a unit of meter cube per second. Then we have E, which is basically the density of electrons per unit volume. Density of electrons is given in meter raised to minus 3. So the unit of tau will be basically meter cube per second into meter raised to minus 3, the whole raised to minus 1. So it will be this and this will go. Second raised to minus 1, the whole raised to minus 1. So it will be second. So recombination, the time scale associated with the recombination rate tau is having given in seconds. Now let us try to solve a problem related to this time constant. So this is basically another time constant. So alpha or tau is given by alpha into number of electrons, the whole raised to minus 1. So the question is, if the recombination rate of a recombination reaction is given as 10 raised to minus 8 centimeter cube per second, then calculate the value of time constant given the electron density is 10 raised to 12 meter raised to minus 3. So basically we want to calculate the recombination, the value of time constant is tau is equal to question mark. Alpha is given as 10 raised to minus 8 centimeter cube per second, which is basically 10 raised to minus 8 into 10 raised to minus 2, the whole cube, meter cube per second, which is approximately 10 raised to 8 plus x is 40, 10 raised to minus 40 meter cube per second. So this is the recombination rate alpha, and the electron density is given as 10 raised to 12 meter raised to minus 3. Now the time constant tau is given as alpha into the concentration of electrons, the whole raised to minus 1, which is equal to 10 raised to minus 8 into 10 raised to 12, the whole raised to minus 1, which will be not 10 raised to minus 8, 10 raised to minus 14, which will be minus 14 plus 12 is 10 raised to minus 2, or 10 square, and then the whole raised to minus 1 will give you 10 raised to 10 square seconds, or is basically 100 seconds. So 100 seconds is the time constant associated with the recombination reaction, which is having a recombination rate of 10 raised to minus 8 centimeter cube per second and having an electron density of 10 raised to 12 per meter cube. So that is time constant. So we learned how to calculate the critical frequency F0, and we also learned how to calculate the time constant too associated with the recombination reaction. Now we summarize the things that we learned about the ionosphere so far. Just give me a second. Yeah. So if we summarize, we can write for practical purposes, the ionosphere can be thought of as quasi-neutral. Because in the ionosphere, the number of electrons and number of ions will be equal. So effectively, the charge will be 0. So that is quasi-neutral, which means the net charge is practically 0. Because the number of the concentration of electrons will be equal to the concentration of ions. Number will be equal. So generally the ionosphere is considered to be quasi-neutral. And the second one, the ionosphere is formed by ionization of the three main atmospheric constituents, which are nitrogen, oxygen, and the atomic oxygen, molecular oxygen and atomic oxygen. So basically, these three atmospheric constituents undergo photoionization to create the ions and electrons present in the ionosphere. And the primary ionization mechanism is photoionization by extreme ultraviolet, extreme UV, and X-rays. The primary ionization mechanism is a photoionization by extreme UV and X-rays. And in some areas, ionization by particle precipitation that we haven't discussed yet. Particle precipitation is also important. The next one, the ionization process is followed by a series of chemical reactions that produce the ions. The recombination removes free charges and transforms ions to neutral particles. So these are the points that should be remembered regarding the properties of ionosphere. The first one, the net charge in the ionosphere is practically zero because the number of electrons and number of ions will be almost equal in the ionosphere. And the ionosphere is formed by the ionization of the three main atmospheric constituents like the nitrogen, oxygen, and the atomic oxygen, molecular oxygen and the atomic oxygen. Then the primary ionization mechanism is photoionization by extreme UV and X-ray radiation. And then that we haven't discussed. In some areas, ionization by particle precipitation is also important. And the ionization process is generally followed by a series of chemical reactions which produce the ions. The recombination removes free charges and transforms the ions to neutral particles. So these are basic characteristics of the ionosphere. Now we will now we know what is the vertical profile of the electron density in the ionosphere. So we will see how to derive or the mathematical expression for this vertical profile. So that is basically given by the Chapman's theory. Chapman's theory. What does it? So we know that this is the number of electrons or number of ions present in the atmosphere, and this is the altitude Z. This is how the vertical profile of the ionosphere looks like. Vertical profile of electron density looks like, right? Now we are basically assuming the number of electrons is equal to the number of ions. So the net charge in the ionosphere is 0, and generally the ionosphere starts from approximately 50 km, or the ions are present in the atmosphere from a height of 50 km. Ions fairly start from 50 km from the surface. And at a height of 250 km, at a height of 250 km, this height Hn, peak density occurs. At a height of 250 kilometers, we have maximum number of electrons. We have maximum number of at a height of ions. At a height of 250 kilometers, we have maximum number of electrons or ions. Chapman's theory, why we have this vertical profile of electron density. So we know Ne is equal to Ni, and then the peak production or the maximum amount of electrons which is present in the ionosphere is 10 raised to 12 meter raised to minus 3, which is basically happening at a height of 250 kilometers. So basically Chapman's theory tells you why we have this kind of vertical profile. of electron density. This is the electron density, this is the height, and if you calculate the plasma frequency at the maximum height, you will get 9 into root of 10 raised to minus 6 NE. NE is 10 raised to 12 meter raised to minus 3. So it will be 9 into root of 10 raised to 12. So it will be 10 raised to minus 6 into 10 raised to 18. It will give you 10 raised to 12. Answer will be 9 megahertz. Will be 9 megahertz. The plasma frequency will be 9 megahertz. At 250 kilometers, the plasma frequency is around 9 megahertz. So we already know that. So now let's look at the basic assumptions for the Chapman theory. Basic assumptions of the Chapman theory. The first one, only one type of gas is there in the atmosphere. First assumption is there is only one type of gas in the atmosphere. So we know that the atmosphere consists of different molecules or different gases like O2, N2, CO2, O3, etc. So the first assumption is only one type of gas is present in the atmosphere. So in the atmosphere we have different types of molecules such as O2, N2, CO2, O3, etc. All these molecules have different cross-sectional area. All these molecules have different cross-sectional area for absorption of the incoming solar radiation. Only one gas is present in the atmosphere. So the first assumption is only one type of gas is present in the atmosphere. But we know we have different types of molecules or gases such as oxygen, nitrogen, carbon dioxide, ozone, etc. And all these molecules have different cross-sectional area for absorption of the incoming solar radiation. So since we are assuming only one type of gas, it follows that the cross-sectional area is the same. Cross-sectional area is basically given by sigma. It is denoted as sigma. Sigma, which is the cross-sectional area for absorption of the incoming solar radiation. Since we are assuming there is only one type of gas, it follows that the cross-sectional area will be the same. Now the second one, is that atmosphere is horizontally stratified. Which means no variation in the horizontal direction. Atmosphere is horizontally stratified. So if we move along the x or y direction in the atmosphere, if whatever parameter we are considering, it won't change. Suppose it is density, temperature, whatever it is, that won't be changed if we are moving horizontally in the atmosphere. But vertically changes will be there, but horizontally there is no change. So at this particular level, rho 1, T1 will be the density and temperature at whatever point you take along the x or y. And at this particular height, it may be rho 2, T2. But vertically it may vary, but horizontally there is no changes, or the atmosphere is basically horizontally stratified. There is no variation in the horizontal direction. That is the second assumption. Now the third assumption is that the incident radiation is monochromatic. Incident radiation is monochromatic. Which means it has only one wavelength. So third one is that the incident radiation is monochromatic. It has only one wavelength. That is the third one. Now the fourth one is that atmosphere is isothermal, which means single scale height. Scale height is H is equal to Kb T by Ng, where Kb is a Boltzmann constant. So if the atmosphere is isothermal, it has only single scale height. So these are the four assumptions in the Chapman theory. First one, there is only one type of gas present in the atmosphere, which means the atmosphere has a single cross-sectional area. The cross-sectional area is the same. Second one is that the atmosphere is horizontally stratified, which means this parameters doesn't change if we are moving along the horizontal direction. The radiation occurs only in the vertical direction. Now the third one is that incident radiation is monochromatic, which means the incident radiation has only one particular wavelength. And the fourth one is the atmosphere is isothermal, which means it has only single scale height. And we have already learned what is scale height. It is the height at which the pressure becomes 1 by E times the surface pressure. So it is given by RP by G or KB T by Ng, where KB is the Boltzmann. Now what are the key terminologies that we are going to use in the derivation? So these are the basic assumptions. Now the key terminologies that we are going to use in the derivation. The first one is Q, is the rate of production of charger ions. Rate of production of charger ions, that is Q. And we have Qm, which is the rate of peak production. We have Hn, which is the height So the key terminologies of the Chapman theory are the following. So Q is the rate of production of charger ions. Qn is the rate of peak production. Hn is the height at which peak production is occurring. Peak production rate is occurring. That is Hn. And we have sigma, which is the absorption cross-section rate. Absorption cross-section area. So the rate of production or Q, the rate of production of charger ions, rate of production we know is directly proportional to the number of neutral atoms present in the atmosphere, present in that particular layer, and is also proportional to the intensity of incoming solar radiation. Intensity of incoming solar radiation. These two parameters are important for the production of electrons or ions. So basically we can write Q is proportional to the concentration of neutral atoms N, and also the intensity of incoming solar radiation I. Q is directly proportional to the concentration of neutral atoms and is also directly proportional to the intensity of incoming solar radiation. So now the intensity of incoming solar radiation is basically determined by the angle at which the solar radiation falls on the Earth's surface, or the time of the day. So suppose this is Earth, and let this be the atmosphere. Suppose the sun is directly overhead. In this case, the angle at which the solar radiation falls on the Earth's surface is 0 only, just like through the normal only, it is directly overhead. And now consider the sun is shining from this side. So in that case, the incoming So in the second case, it is making an angle with the normal, which is given by chi. So when it is directly overhead, chi is equal to 0, and here chi is some number. When sun is overhead, chi is equal to 0. So chi is basically the solar zenith angle. Chi is basically the solar zenith angle. So when sun is directly overhead, chi is 0, and if sun is at some other point, chi will be some value. Chi will be a positive value. So when sun is not directly overhead, it is at some other point. In that case, in this case, the sun's radiation, the solar radiation, has to travel larger distance. Has to travel a longer distance to reach the surface of the Earth. Solar radiation has to travel longer distance to reach the surface of the Earth compared to the distance when it is directly overhead the Earth's overhead the surface of the Earth. So if we take an air column that consists of n air molecules with a total, the total cross-sectional area will be n sigma. So consider an air column over here like this. The number of molecules present in this particular air column is n, and we discussed the absorption cross-section. We are considering it as sigma. So in that case, the total cross-sectional area is n sigma. Now I'll draw it again. Suppose this is sun. This is the surface of the Earth. This is the first case when it is directly overhead. This is the second case when it is at down. So this angle is given by chi, or the solar zenith angle. This is chi. Okay. So let's consider a vertical distance. Let this be dh, and in this case, this distance be dx. Okay, this is chi. Now from the now we are taking a small incremental height dh in the vertical. So now the relationship between dh and dx can be written as dh from this right angle triangle. This is dh, this is dx, and this is chi. So cos chi can be written as base by hypotenuse, which will be this is a right angle triangle. Hypotenuse is dx and base is dh. Dh by dx. So dh can be written as dx cos chi, or we can write dx as dh sec chi. Let this be equation 1. Now the maximum solar radiation will be at the top of the atmosphere. So this is the point at which we have maximum solar radiation, which is I infinity. The decrease in the intensity of radiation. The decrease in the intensity of radiation from top. The decrease in the intensity of radiation from top is given by, suppose di is the intensity of the change in the solar radiation. Di is the change in the incoming solar radiation with respect to height. Di is given by I into A d x into rho. I is the intensity of incoming solar radiation. A dx is the volume that the solar radiation is encountering as it is on its way to the surface of the Earth, and rho is the density of neutral atom in that vertical column. This is the density of neutral atoms. Density of neutral atoms is rho. A dx is the volume of the air column, volume of the air column, I as the intensity of incoming solar radiation. So IA dx into rho. So dx we know. So the change in the intensity of incoming solar radiation as it reaches the surface is given by di is equal to I into A dx into rho. And we earlier from the right angle triangle we got dH is equal to dx into cos chi, or dx is equal to dH into c chi. If we substitute dx here, it will become di is equal to a I a dH c chi into rho. And we know rho is basically the density of the neutral atoms is basically rho 0 e raised to minus z by h. In this case, vertical distance is given by small h minus h by h. So rho can be written as rho is equal to rho 0 e raised to minus h by h. So it will become di is equal to ai rho 0 sec chi into exponential minus h by h. So we are basically finding how the intensity of radiation is changing with respect to height, right? So di by dh, di by dh will be ai rho 0 c chi into exponential of minus h by h. So we can write di is equal to ai into rho 0 c chi exponential of minus h by h. How the intensity is basically changing with respect to height. So let this be equation 2. Now if we integrate the equation from I infinity to I, if we integrate the equation from I infinity, which is the intensity of incoming solar radiation at the top of the atmosphere, to I, which is the intensity at a particular height h, it will become integral I infinity to I h di is equal to integral h is equal to infinity to h is equal to h a rho 0 c chi exponential of minus h by h dh. I, when I is there, that will take here. This I is taken to the left hand side. So it will become integral I infinity to I h di by I is equal to integral infinity to h a rho 0 c chi into exponential of minus h by h into dh. Now if we integrate it, it will become log of I by infinity. Integral of di by I is log I. So log I by I infinity is equal to a rho 0 c chi into e raised to minus h by h into minus h, which will be h2. Integral of dh is h itself. It will become minus a rho 0 c chi into e raised to minus h by h. Once we give the limits, it will become into h. Since e raised to infinity is equal to 0. If we substitute infinity, it will become 0. So we can write I is equal to I infinity into exponential minus a rho 0 c chi into e raised to minus h by h into h. So this is how the intensity of solar radiation is changing with respect to height as it reaches the there is an exponential. So since there is an exponential term with negative, it basically denotes the exponential decay of the intensity of solar radiation. So the basic purpose is we need to find Q, which is the production of ions or electrons in the atmosphere. So basically we need to find Q. So Q at any height h depends upon a the solar zenith angle chi and b number of electrons eta per unit volume. We already discussed that the production Q at any height depends upon the solar zenith angle and the number of electrons or ions present per unit volume. So we can write Q as which is basically a function of the solar zenith angle and the number of electrons Q and chi. Q and H. Eta into di by dh into cos chi. This is equation. Eta is the number of electrons per unit volume. Number of electrons or ions per unit volume. Di by dh is the change in the intensity of solar radiation with respect to height. So this is the equation for the production Q. Now please substitute differentiate equation 3. Differentiate equation 3. Equation 3 is the equation which gives you, let this be equation 3. Which basically gives you what is the intensity at a height h. So if you differentiate equation 3, it will become, so LHS is having I, it will be di by dh. Di by dh is equal to I infinity into exponential of, we have minus a rho 0 h c chi into e raised to minus h by h into minus a rho 0 c chi into e raised to minus h by h into minus 1 by h. Differential of the potential is e raised to tau. So it will become di by dh is equal to I infinity into exponential of a rho 0 so it will become I infinity into I infinity di by dh is equal to I infinity a rho 0 c chi into exponential of this term minus h by h minus this term a rho 0 h into c chi a raised to minus h by h. It will become like this. Now if we substitute di by dh, this di by dh, let this be equation 5. So if we substitute equation 5 in 4, it will become q of q, which is a function of the solar zenith angle and the height, will become eta into di by dh, right? So eta into I infinity a rho 0 c chi into exponential of minus h by h minus a rho 0 c chi into h into exponential of minus h by h into cos chi. C chi and cos chi will go and it will become q of chi h is equal to eta into I infinity a rho 0 exponential of minus h by h minus a rho 0 h c chi into e raised to minus h by h. So this is the equation for the production of electrons or ions at the height h. So it gives the production rate of electrons or ions at a particular height h and attaining solar zenith angle right. So basically the peak production depends upon the number density of electrons, which is eta, intensity of incoming solar radiation. A is basically the area of cross section, that how much distance it's basically using how much distance the solar radiation is traveling to reach this particular height h. Rho 0 is the surface density, then exponential of then h is the height at which we are considering. C chi is there, which is the solar zenith angle. So it depends on all these factors. So this is the equation for the production rate of electrons or ions at a particular height h and at any solar zenith angle chi. Okay, I think we'll wind it up over here today. So today we looked at what is the significance of solar radiation, what is the significance of ionosphere when we are basically considering radio wave propagation, why we are using ionosphere for how is it useful for radio wave propagation, and we also learned what is the how should we determine the frequency of the radiation, frequency of the radio wave to based on the distance between the two towers. And we also learned about photoionization, then the critical frequency at which the radio wave should be sent for it to reach at a particular, for it to travel at a given distance. So critical frequency is found to be a function of the electron density. number of electrons, which is Ne, is given by H0 equal to 9 into root of 10 raised to minus 6 into Ne. And we also learned what is recombination and the different types of recombination reactions. We also learned the time constant associated with the recombination reaction is given by tau is equal to alpha into concentration of electrons, where alpha is the recombination rate and density of electrons. Then we started Chapman theory. We learned what are the basic assumptions of the Chapman theory, and we finally derived a mathematical expression which gives that the production of electrons or ions at a particular height h if the solar radiation is incident on the Earth's surface at the solar zenith angle. Right. I think that is enough for today. Yeah. So we will find